In this video, I'm going to be introducing how to find the volume of a solid. There's a lot of different methods to do it. So we're going to start off with the most basic method called the disk method. So what do I mean by the volume of a solid? Well, in calculus, we can start to really think about volume in a pretty complicated way. We can think of the height of an object being the output of a function. And if we think about that function spun around an axis, either the x-axis or the y-axis, then what ends up happening is it creates this solid type shape that has a volume. So the most basic form is that we have a rectangle. It has a height, which is equal to the output of our function or the value of the function. And it has a width equal to the change in the x values. And if we spin that rectangle 360 degrees about the x-axis, spinning it around the x-axis, it creates this cylindrical shape called a disk. And we can find the volume of this disk by finding the volume of a cylinder, essentially. And the volume of a cylinder is the area of the circle times the height. So the area of this circle, which is pi r squared, times our height, our w or our width, change of x. So what does that look like in terms of a function? Well, remember that the height is the output of the function, and in this case, it represents the radius of our disk. So if I take our function and square it, rather than taking the radius and squaring it, and then I multiply by my change of x or my width, and then multiply by pi, then we get the volume of the disk. So the volume of a cylinder, in a lot more complicated calculus notation, becomes the volume of a disk, and it looks like this. So we can do that, find the volume of our solid by rotating it around the x-axis, and we would do all of our math in terms of x, but if we were to spin it the other way, if we were to rotate it around the y-axis and use horizontal rectangles, it would be almost the exact same thing except in terms of y. So we'll do a little bit of both. It's really a good idea or a nice way to do it if you visualize your problem first. So either using a graphing utility or just a quick sketch of what the graph looks like and what it may look like when you start to rotate it about an axis. So we're going to take this graph, x squared minus 4x plus 5. It's a parabolic shape. We're going to talk about the area underneath that graph on the interval from 1 to 4. But then we're going to spin that. And when we spin it about the x-axis, it creates kind of a vase-looking shape here. And we can find the volume of that by using a bunch of disks, actually an infinite amount of disks. So I'll show you what that looks like in a quick visualization here. So this is the disk method. We take a function and we spin it about the x-axis and we fill it up with a bunch of disks. And in finding the volume of all of those disks, we add them up and we get the volume created by spinning this graph about the x-axis. In order to do that, we use that formula where we square the function, multiply it by pi after we integrate and find the volume underneath, or the area underneath the curve. So the first thing to do is recognize your function, recognize the interval. That interval is going to be our bounds when we integrate. Since we're doing pi r squared is the function, so we got to square our function being used. Sometimes that's easier than other times. Sometimes it's more difficult. If we want to square this trinomial here, write it twice and distribute, and this is what we end up with. So that's what I'm integrating. We're going to find the antiderivative of that. We get this, and we're going to evaluate that from 4 to 1, or from 1 to 4. Plug in 4 first, and then subtract it when we evaluate 1. And once we get all of that, then we're going to multiply by pi. So multiplying by pi will be our last step. So if I plug in 4, I get this. If I plug in 1, I get this. I'm going to evaluate and subtract those two values. We could use fraction math. We could use our calculator and do decimal form. Just make sure that we're keeping up to 3 decimal places as we work so that we can keep our accuracy. So either in fraction form or decimal form, we end up with these two answers, attaching pi to the very end. Let's try another example. Let's try it with a trig function. We're going to find the volume of the solid created by the square root of the sine of x and y equals 0, which would be the x-axis. And we're only going to do it on the interval of our inputs from 0 to pi. So you can find the intersection on the interval from 0 to pi, but essentially the zeros of the square root of sine of x are 0 and pi. And we can visualize that on our graph. So we're taking this top graph, which is the square root of the sine of x, and we're rotating it around the x-axis. So we get its symmetrical image on the bottom. So you can think of this as like a football shape. And we're going to try and find the volume of it. So we take our function squared. Our function is the square root of sine of x. And if we square it, we just get the sine of x. And we're going to integrate that from 0 to pi and then multiply that by pi. So find the antiderivative of sine of x, which is negative cosine of x, and evaluate it at pi, evaluate it at 0, and subtract those two values. And eventually we get 1 plus 1, which is 2, times pi is our last step. So the area is about 2 pi. One more example. This time let's use our horizontal rectangles and revolve a solid around the y-axis, just to see that it's really not that much different. So this time we have a graph in terms of y. And you can actually visualize this in terms of x. You could solve for y, and you would actually get the same graph. So it actually has a slope of 2/3. What we're doing is we're taking that graph, we're finding the area underneath it, or the area in between it and the x-axis, and we're going to spin it around the y-axis. So this is spinning this direction now. So it's being symmetrically spun over here as well. So we can visualize both those parts. If you can visualize this spinning, it's actually creating a graph that has a big hole in the middle. And so we're going to find out in our next video what a better method would be to approximate the area of this. But in this video, we're just using the disk method. So this disk method is not essentially the most accurate way to find the area, but we'll do it anyways. So one thing you want to find is make sure that you know your intersection points here. So this time we're finding the intersection of the y-axis. So this graph from 0 to 3 actually intersects up here at y equals 2. If we solve this, set it equal to 0 and 3, then we could find our two intersection points at 0 and at 2 on the y-axis, right? These are y values. Everything's in terms of y here. So we can integrate. First, we're going to square our function, and then we'll integrate it in terms of y from 0 to 2 and multiply by pi. So squaring this function, we get 9/4 y squared. Find the antiderivative of that, and we get 3/4 y cubed. We'll evaluate it at 2. We'll evaluate it at 0. Subtract those two values. We get 6, and multiply by pi for your last step. So the approximate area is 6 pi, but we'll learn in the next video that if we use a different method called the washer method, we'll actually get a much more accurate answer. But there's an example of rotating about the y-axis. Everything's the same, just in terms of y.